what I did.
Well, on the first page is not NMR. That's obviously IR, yeah? Document camera. I think we'll just slide out down here. That's going to be the best. If you ever can't see, please yell. Okay. You should know IR from Organic 1. Okay. Here's two alcohols at the top: a primary alcohol and a secondary alcohol. There's two IRs. Which alcohol goes with which IR? Well, I have no clue. That's because both alcohols have an OH. Well, both IRs have an OH, yeah? Both alcohols have saturated CH, which is going to be just below 3,000. sp3CH. Both IRs have that. Both IRs have a fingerprint. Now, the fingerprint's different, but unless you had something to match it up to, you can't tell. I don't know which is which. IR has limitations. IR will show us the functional groups, but we can't tell the backbone. NMR can tell more precisely the entire structure and the backbone. For example, here's an IR. How many CHs is this for? It could be 1, 5, 20. Well, guess what? In NMR, you can tell exactly how many hydrogens you got. Different types of NMR. You have HNMR, or we'll call it proton NMR. That's when you look at the hydrogens. We'll also do carbon NMR. That's when you look at the carbons. But there's other types of NMR, like fluorine NMR, or something exotic like boron NMR. So, we flip the page, we see examples, the NMRs of those two alcohols. I'll show the top one, you've got the bottom one on your paper. Okay? We're in introductory mode until I tell you we're going to get into it a little bit more. Intro mode here. Here's an NMR. First off, to kind of orient you. Okay. Baseline is in ppm, that's parts per million. We'll talk about what that is. NMR is a type of spectroscopy. Spectroscopy, you use light. IR, what type of light do you use? Duh, IR light. What type of light do you use for UV vis? Duh, UV vis. What type of light do you use for NMR? Not NMR light. What type of light or radio frequency? I'm sorry. Yeah. What type of electromagnetic radiation? We use radio frequency. The same type of electromagnetic radiation that you tune in your radio station with. And if you look at a electromagnetic spectrum, radio frequency, is that on the high energy end or the very weak end? It's very weak. Got long wavelengths. What's on the strong end? X-rays, gamma rays. Okay? No, we're using radio frequency. Do we plot frequency or wavelength here? Actually, no. We plot ppm. We'll talk more about it. What do you plot in IR? Do you plot wavelengths? Wave number, which is reciprocal wavelength, reciprocal centimeters. So what are you plotting? But ultimately, the variation is ultimately a variation in wavelength or frequency. Okay? But we'll have to figure out what ppm means. All right, before we move down to the one below, I already told you which goes with which. This is the primary alcohol. I've actually also already put A, B, C, D on there. That refers to how many different types of hydrogen are in that primary alcohol. Four. That's what the A, B, C, D is. You've got the CH3 on the end. That's A. Those three H's are identical. That's one type. Then you have these two here. Are they the same as the CH3 on the end? No. They're closer to the OH group. Just that right there makes them different. They're chemically different, but they're also going to end up being magnetically different. C. That's a CH2, right? That's a CH2. Are they the same? No, clearly that's different. That's bonding to oxygen. It's going to experience more of an electron withdrawing effect. By the way, that's the CH3 is called a methyl. What's the CH2 called?
I don't expect anybody to know this. It was not mentioned in organic 1.
CH2 is called a methylene. Methylene is actually spelled methyl, but it's got an E-N-E on it. Methylene, E-N-E. Okay, two methylenes, they're not the same. What's the fourth type of hydrogen? The one on the O. Don't forget about H's on O's and N's. Okay? Well, guess what? 4 types of hydrogens is going to give 4 signals in the H NMR. We're doing H NMR here. I'm looking at H's. Here are your 4 signals. 1, 2, 3, 4. What we'll see with these signals is they have terminology associated with them. This signal that's a T. That's my T. So T stands for triplet. All this will be written down later. Okay? This is a triplet. Why is it a triplet? Because it's the number of lines that make up the signal. 3 lines. 1, 2, 3, triplet. We say the signal has been split into a triplet. The 2H means that's for 2 hydrogens. We can quantify here. This is a singlet for 1 hydrogen. It's a little bit broad at the baseline, but ultimately it's just one peak. This guy here is a multiplet, M, for 2H. I see 1, 2, 3, 4, 5, 6 lines. Probably should be more than that. There's probably some overlapping. When you get above 4, most people start calling it a multiplet. This has 3 lines, and does its what? Triplet. That's for 3H. How do you know it's for 3H? Well, we'll talk about how you determine that. That determination is really not present here. You expect 4 signals for hydrogen. Here are your 4 signals. Now, I've already assigned peaks. This is the C. That means that's that methylene right there. Indeed, what we'll learn is, well, let's start by asking you this. Of B and C, which one is experiencing a more electron poor effect? The electron withdrawing effect of the oxygen is more prevalent towards B or C? C, because the oxygen is attached to C. C is a more electron poor. The oxygen's closer, it's pulling on it. That oxygen's a greedy SOB. Okay? Likes those electrons. C is electron poor. What we will learn on the next couple of pages is the more electron poor the environment is, the more likely the signal is to be downfield. C, more downfield. B is not going to be as much downfield. And B is actually here. Then A doesn't experience the pulling of the oxygen as much. A is actually more upfield. What is the signal here? Well, that's D. That's the OH. OHs can be variable. Why are these split? We'll cover that as a particular section a little bit later. If you have questions, just shout it out. Look below. Let's do that one. I would ask you how many different H's, but the answer is already given. You see from the structure that it's what? 3 in this case. Why is it 3 and not 4? And you got H's, 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 H's. Why is it not 4? Because of symmetry. Because that CH3 and this CH3 are the same due to symmetry. They're both bonded to a C that has an OH on it. Have symmetry. You always got to look for symmetry and determine how many signals. Okay? How many hydrogens are ahydrogens? 6. 3 and 3, 6. You expect a signal that integrates for 6. And indeed, where's it at? Right there. It turns out it's a doublet. We haven't said why. That's the A signal. How many H's on the B carbon? There's one H that is a B. There it is. Somebody tell me why that signal is more downfield compared to the A signal. The oxygen is there and it's pulling. That oxygen pulling, we're going to say it's de-shielding. And de-shielding, we're going to say, shielding, de-shielding is sort of analogous to sunscreen. If you put on sunscreen and go out to the sun, you're shielded. So let's think about this analogy. If you have on sunscreen, do you feel the sun's effect as much? Does your skin get the full effect of the sun if you have on sunscreen? No. The sunscreen shields you from the sun. Here we're going to say that electron density shields you from the magnet. B does not have as much electron density. So it's not shielded. What's the opposite of shielded? It's going to be de-shielded. B is more de-shielded because of the oxygen. The electrons are not there. De-shielded is going to be that way, downfield. We're going to state this stuff in a minute. So, the NMRs of these two, once you learn NMR, you can quickly tell them apart. Where with IR, I have no idea which goes with which. IR has limitations. HNMR and then carbon tells you more about the backbone and quantifies the number of hydrogens or carbons. It also helps you put together the structure when we talk about that splitting. Okay, next page. That's just an example of melatonin. There's an IR at the top. There's an NMR at the bottom. Once we cover NMR more, you can look back at this. Let's not spend any time down. What's melatonin? Sleep hormone type thing. Yeah. Okay, spectrum overview. Isn't it amazing how these relatively small organic molecules can do so much in the body or in the drugs or so much in industry? These are fairly small molecules. Okay, here's just another spectrum. HNMR typically 0 to about 10 to 12 ppm. When we get to carbon, that'll be 0 to about 200. Okay. Here's a compound, benzylamine. Let's not talk about number of signals, but it's got the benzene, protons on the benzene ring are here, more downfield. There's 5 of them. They're actually not equivalent. Sometimes you get peaks, it looks like one signal, but it's actually two or three that are on top of each other. We'll talk about that. This is the CH2 here, and this is probably the NH2 here. TMS. TMS is internal standard. It stands for what? Oh, it's on the page, huh? There it is. Tetramethyl silane. All of these methyls are equivalent, so there's only one type of hydrogen and thus only one signal. And it's actually a singlet. We set that at 0. Typically you need some type of internal standard when you do NMR. The IR, you never have to worry about this because the instrument sets the 4,000 point, and there's no variation. NMR, because we're dealing with a magnet, we haven't talked about that yet. The strength of the magnet, which we have one on the 3rd floor, the strength of the magnet can vary day to day. Just like a radio station. If you got an old radio where you tune it in with a knob, one day it's good, the sound is good. You come back the next day and it's a little fuzzy. That's because the signal power has changed a little bit, and you have to tweak it, get it come in better. You guys old enough to know these types of radios? It's like that, because the tower, the signal can change day to day. Because of that, we can talk much more about why, but to account for that, we include a standard and we say, okay, I'm going to set that to 0, and now everything else is relative to this being at 0. Now, terminology, I've already mentioned some. Down here, this is protons and electron poor environments. The more electron poor environment, the more it's going to be this way. Didn't we state that? We did. Video record right there. On the flip side, protons and electron-rich or in dense environments are going to be more to the right. The signals will be more to the right. This way is called de-shielded protons. What's that way? Shielded. What shields the protons? Sunscreen? Electron density shields it. See, this goes hand in hand. Electron density shields the proton just like sunscreen. Okay? This is called downfield, that's called upfield. A lot of students think that this is upfield because the number gets higher. Actually not, this is downfield. The downfield actually refers to the magnet strength. And depending on, in the old days, as you swept through, you didn't change the frequency, you kept that constant. What you actually changed was the magnet. And you scan through, and for it to give a signal, for like those H's to give a signal, that signal didn't show up until you turned the magnet down. So this became known as downfield.
The one coming over here.
All up there. What we got? In terms of frequency, again, we don't plot frequency or wavelength, but this is indeed high frequency. That's low frequency. I don't know that if that's even going to become relevant at all. Perhaps because we do know that frequency, what's the high energy in? It's high energy in. So it's good to know, but it's not as important as this terminology. Delta values. This peak is said to occur at like 7.25 ppm. You can also say that the delta value is 7.25. To me, that's kind of formal, but you'll see it in like the literature. What's the delta value? For me, I just say ppm. And of course, a large delta value means a large ppm. Sample prep, I didn't bring the tube. A few milligrams or more. With NMR, you have to dissolve the compound. When you do IR, you just put the compound on the IR. Okay. At least today, you still have to dissolve it. I mean, people are working on trying to do solid phase NMR stuff, but you dissolve it in a solvent that doesn't give any NMR peaks. It doesn't give many. Old-fashioned common solvent was carbon tetrachloride. How many signals would this give in the HNMR? It wouldn't give any, would it? It didn't have any. So it's good. You don't want a big solvent peak in your spectrum. You only want your compound in the spectrum. Problem with carbon tetrachloride is that, first off, it's more toxic than other things. Also, because it's nonpolar, it's not a great solvent for a lot of stuff. If your compound has any polarity at all, it's probably not going to dissolve in carbon tet. We can go to CHCl3. Okay? What is this called? You can at least say trichloromethane, right? But nobody calls it trichloromethane. What do we call it? It was used in the Civil War. Queen Victoria inhaled it when she gave childbirth, and chloroform. Yeah. Chloroform is polar because it doesn't have dipoles, don't cancel. Problem is it now has this H, and it'll give a signal in the H&MR. And because the solvent is a lot compared to your small compound, small amount of your compound, that signal will be huge. So then chemists said, well, what can we do here? We need a polar solvent, but we don't need H's, so chemists replaced this with a deuterium. And that's CdCl3. What is a deuterium? Isotope of plain hydrogen. Plain hydrogen is 1, atomic number is 1. And plain hydrogen, the most common hydrogen, has no neutrons. And so the mass number is what? Also 1. Deuterium, first off, it's an isotope of hydrogen. Every isotope of hydrogen has mass atomic number 1, but deuterium has 1 neutron. So what's the mass number? 2. This equals deuterium. Now it is a hydrogen. It does give an NMR signal, but this type of hydrogen doesn't give an NMR signal in this range. Okay? A lot of students think that deuterium doesn't give an NMR signal. It does, but we just don't scan it in range. And on the next page, we'll learn how to predict if this does or does not. By the way, this is a hydrogen, standard hydrogen. How many protons? 1. How many neutrons? How many electrons if we're dealing with a standard neutral H? 1 electron. What if this becomes H plus and it loses the electron? And we get rid of that. What is this now? All it is 1 proton. That's why an H is often called a proton. Okay, CdCl3. This is where DMSO, which is methyl with the SO, we saw that this morning, right? That's thionyl chloride. If this is 2 methyls, it's called dimethyl sulfoxide. It's a great polar solvent. You replace the H's with D's. It's my favorite solvent. Solves polar compounds. It's great. Much more expensive. All those deuteriums had to get on there. You dissolve it up. You place it in an NMR tube, which is about the size of a straw, about 7-inch slender, long glass tube. Put a cap on it. You may insert some TMS as an internal standard. There's other tricky ways to do internal standards. If you're wondering why I said often and not always. Then you put the sample into a magnet. We may take a look at the magnet on the 3rd floor. Putting the sample into the magnet, you guys know MRI at the hospital? What do they slide the patient into? Magnet. Okay. The ideas behind MRI are the same. MRI used to be called NMR. But in the beginning of this technology, people heard nuclear magnetic resonance and they were afraid of nuclear. Well, it turns out nuclear doesn't mean like nuclear at the plant or something. Nuclear just refers to the nucleus of the atom. Guess what? Everybody's got nuclei in their body. Okay? But the common person that didn't know science was afraid of nuclear. So they changed the name to MRI. Magnetic resonance imaging. And it's amazing how they can do NMR on your body. They're doing the NMR of water in your body, the H's of the water. And apparently the water in different tissues gives different signals, or somehow they turn that into an image. And to me it's miraculous. I don't know how they do it or I don't know much about it. They turn these into images. Combination of mathematics, physics, and chemistry. Get to that point. Okay, any questions about believe it or not, that was kind of the overview. That was the intro. Now we're going to get into it a little bit deeper. Any questions about the intro at this point? some of the terminology making sense already? Okay, the NMR phenomenon. How do we get signals? What type of atoms will give signals? We pretty much have already stated this. N deals with the nucleus of the atom. Magnetic deals with the magnetic properties of the atom. Believe it or not, atoms have magnetic properties. Resonance just is a fancy word for when the absorption takes place and everything comes into sync. You get a peak. NMR. Okay, the NMR phenomenon that I call. First off, what type of atoms can you do NMR on? The nucleus has to have a net spin. Quantum spin number. A spin quantum number greater than 0. Spin quantum number is usually denoted as the capital I. The nucleus has to have an I greater than 0 to have a magnetic moment, to have magnetic properties. If I is 0, you can't do NMR on it. But if it's not 0 and it has a spin, nucleus has a spin. What's the charge of a nucleus? Is it charged? It's positively charged. It has protons. I haven't had physics in a long time, but a charged particle that's a spin, what does that create? A magnetic field. Okay? The nucleus has a magnetic field. That magnetic field has a direction. Okay? Direction can be illustrated. But if it doesn't have a spin, it doesn't have that, and you can't do NMR. Those that do have a magnetic field, we can probe that, and we can get NMR of it. Mark?
How do we know the spin quantum number?
Good question. This is the next topic. How do we know? You're not going to know the spin quantum number, but you're going to know more broadly that. Any nucleus with an odd number of protons or neutrons will have a spin quantum number greater than 0. What you really want to ask is, does it have an odd number of protons or neutrons? If it does, you can do NMR. How many protons? Is that odd or even? Can you do NMR on that? Yes. By the way, well, game over. That's all you need. All you need is one of those. And by the way, the spin quantum number of this is 1/2. But you don't. I would have never told you that unless you had asked. Can you do NMR on this? How many protons? One. You can do NMR. All it takes is for one of those to be odd. By the way, the spin quantum number of deuterium is actually 1. That's 1/2, and that's 1. So those were there. Carbon. First, what's the standard carbon? Standard carbon is carbon 12. Can you do NMR on standard carbon? Every carbon is 6. Sometimes you won't even see that 6 shown. The superscript is your mass number. Okay. If this is not shown, you have to look on the periodic table or just know it's 6, right? How many protons?
6.
How many neutrons?
6.
Either one of those odd? Sorry, you can't do NMR on it. Can't do NMR here. How about this one? Can you do NMR on standard oxygen? No. 8 and 8. No. How about carbon 13? 6 protons, how many neutrons? 7. Good. You can do NMR. And when we do NMR on carbon, we're doing it on C13. Now, what's natural abundance of carbon 12 and 13? On day 1 in Organic 1, I put this on the board.
Isn't it 1?
Yeah, natural abundance percentage for carbon. 99% of the carbons in your body are carbon 12. 1% are carbon 13. Of any sample, only 1% is carbon 13. But if you do carbon NMR on it, that 1% is what you're doing the NMR on. Because of that unfortunate percentage, it's not in our favor, Doing carbon NMR takes a longer time, more sample. Usually when I run carbon NMRs, I run them overnight. Can you imagine running an IR overnight? I mean, you guys just boom and it's done in 4 scans. When I do carbon NMR, I do like 10,000 or 20,000 scans. Proton is naturally abundant. It's in your favor. It's quick. You can do it in 15 minutes. Okay. Others that you can do, how about this? It's in this row, so obviously you can do it. How many protons? 9. Okay. Yes. Fluorine NMR is actually also real easy because all fluorines are 19. 100%. There are fluorine 18 out there, but that's man-made. You have to generate it. And what's F18 used for? Anybody know F18? It's used for PET imaging in the hospital. When you go to nuclear medicine, they use F18. They make F18 over on Central Avenue. They have a small cyclotron. But F18 is not natural. Would F18 be NMR active?
No.
No, it would be.
Sure, it would have 9 protons and 9 neutrons. Both would be odd. It'd be doubly active. It's not doubly active, it's active. Problem is, F18 has a half-life of about 110 minutes. That's why that's a difficulty with PET imaging. They have to generate the fluorine nuclide right on the spot. You can't store that stuff. It decomposes. Okay, O17 you can do. I don't know what the percentage is of O17. It's real small of natural. Breathe in oxygen. Everybody take a deep breath. Probably about 0.5% of the oxygen you just breathe in is O17. Majority of it is O16. The senior professor I worked with at Georgia State as a postdoc wrote a book on O17 NMR. Okay. So how do we get a signal? Now we're going to get into the deep theory a little bit. And then we'll go back to the spectrum. How do we get a signal? With IR, we talked about signal and vibration. Okay. If you had a sample with hydrogen in it, you'd have gazillions of hydrogens in there. Gazillions of hydrogen nuclei. All those nuclei would have a magnetic moment. But they would all be random, with a direction going everywhere. Okay? But it turns out if you place the sample with the random nuclei going everywhere in the presence of a larger magnet, and that's denoted with this here, with the magnetic field going that way. If you put it in the presence of that, these will orient themselves either in line with the magnet, which is what this is, or oppose. Now, those that are in line with it are lower in energy. Those that oppose are higher in energy. This is called the alpha state, that's the beta state. So now we put this in a magnet, like we slid the patient into a magnet. The nuclei line up. What is this like? This is just like a compass. If you came from outer space and you came to Earth, what would the compass do? It would feel the magnetic field of the Earth, and it would line up. It's the same idea. Okay. Now, do you ever see the compass line up the opposite way? Like this? I don't think you do, do you? That's because the energy there is too big. The energy gap is too big. Here, this is actually a very small energy gap, and so you do get some that will line up that way. And to ask why, you'd have to go to somebody like Dr. Zuckerman who gets into physical stuff or a physicist. It's actually a good analogy. If you're ever canoeing, your canoe you can face it downstream and you'll be okay. What if you turn the canoe sideways? It'll torque you back to downstream. But you can actually turn your canoe upstream and be better than sideways. Okay? Now that we have these two states, you've got to have two different energy states. But you only have that in the presence of the magnet. Now we can put energy into this state, and it'll actually flip and do a spin flip and absorb the energy. Because to go here, it has to absorb energy. Okay? And that's probably below. We can put energy in, H nu, light energy in, do a spin flip. That would be called, the system would do an absorption. But also, and you could plot the absorption. The other term is, this will actually decay and give off the same amount of energy and come back down to the alpha state. That's called relaxation. That's the energy coming out. Okay? And actually in the modern spectrometers, this is what we measure, the energy coming back out. The reason I point that is because later on we'll talk about relaxation rates. Okay, so let's pause and let me ask you, why do we get different signals? I mean, here, this is, we already said that we expect A, B, C, D. Why do we get 4 signals? First of all, isn't all this compound in the magnet? And when we put it in the magnet, how many H nuclei do we have here? 3, 5, 7, 8. 8 hydrogen nuclei. They're all going to line up either with the magnetic field or against it. And then we can do a spin flip. But this might be a certain amount of energy, and this is a certain wavelength. And it's just a single wavelength. I mean, if all the H's were the same, you would just get absorbance at one place, and you wouldn't get different peaks. Why do we get absorbances at different places for different hydrogens? Go ahead. Good, that's the first point. The gap for different H's is different. Some may have a gap like this, where you flip there, but others may have a gap like this. And this takes more energy to do the flip. Because it's more energy, it's going to be at a different part of your spectrum. So why would some have different gaps? You're good at sort of seeing what we said earlier, and yeah, it's going to end up being because of electron density. But why? Why does that cause different gaps? Well, flip the page. Okay, the stuff up top is just kind of for reference. You can look at it. No need to read it to you. I'm not going to explain it. Let's go to this graph. This graph illustrates an important point. And it helps us with the variation here. Yeah. Okay, we have energy here. Once this level split, we have delta E, which is the difference in energy. This is B naught, which is your big magnet strength, usually called B naught, the original external field. What if B naught was 0 and we're here? That is, there's no external field. What's the energy difference between your states? 0. You don't even have 2 different states, do you? If the magnetic field is 0, you don't even have 2 states. What if the magnetic field thus is maybe arbitrary number 1? Now you have a magnetic field, and you should get a difference in you should now get 2 states. Well, What if the magnetic field gets bigger? What happens to the gap between your two states? It gets bigger. The bigger your external field is, the bigger your magnet, the bigger the gap between the alpha and the beta. Which one of these scenarios is experiencing more magnet? On the right. Yes. Go back to the analogy of the sun. Which one's experiencing more magnet? That one. That's like experiencing more sun. What if we put sunscreen on this proton? Is it going to feel as much sun?
No.
No, it won't feel as much magnet. The gap will get smaller. How can we put sunscreen on a proton?
Shielding it.
It's the electrons that act like sunscreen. So it goes back to difference in electron density is going to cause different gaps. Now, how is that shown formally on this page? It's an equation that you sometimes see, and if you read it first, you're like, what in the world do they mean by all this? Ultimately, we don't want to say what type of magnet we're in. We want to say, what type of magnet is this experiencing? It's like if you two go to the beach, we don't want to say, what type of sun are you under? You're under the same sun. We want to ask, who has on more sunscreen? That's going to lead to the difference. You're both in the same magnet, but the B local can change. The electrons produce their own magnetic field. And it turns out that it opposes this. And that opposing acts like sunscreen. It diminishes this. But because this varies, the net result varies. This is electron density. The local magnetic field of the electrons opposes the big magnet. So that's how you get different left here. This would lead to two different signals, two different absorbances, and that's shown at the bottom. This is not experiencing as much magnetic field, so the gap is smaller. They're saying that that is this signal. This is experiencing more magnetic field because it's, is it shielded or de-shielded? We would say that's de-shielded, because if it was shielded, it should experience less. That's shielded compared to that, right? That's de-shielded. Shielded so it doesn't see as much magnet, the gap is lower. But where's this signal going to be on the ppm? It's saying it's more, what's the terminology that way? Upfield. Does that make sense? In terms of shielding. Is this shielded or de-shielded? Shielded, because it's not experiencing as much magnetic field. Which way did we say shielded was? Upfield, you see? That's de-shielded, thus it feels more of a magnet, and the gap is bigger, and the peak is ultimately going to be down here. And the reason you had to turn the magnet down was it experiences more magnet. And thus you had to turn it down. That gets complicated to explain. Okay. That's the theory. Believe it or not, it's really only F. We really didn't say how the absorption took place. We set up how the absorption, we really didn't say how this happens. We just showed that it could. Now, if you get into advanced NMR, you'll learn how this actually happens. And you talk about precessional frequencies. I might send out a video, and you can watch it or you don't have to. For those who are interested in this type of stuff in physics, I've never seen it, I learned. It's a guy, he spins a wheel, and then he torques it. He shows different things. That gets into that. I'll send it out. If you think it's going to confuse you or something, maybe watch it. Okay? I think it's neat. Okay, there's main concepts to cover. There they are. While you're looking at them, let's take a short 4-minute break. Stand up, stretch. Third grade, we used to do finger exercises like this. Miss Henderson would, I don't know why, just to loosen up our fingers. And we would say exercises, exercises.
What figure?
I don't remember, it was something like that. You do that in third grade?
450.
I remember that. I remember I threw a paper plane into an air conditioner vent and got in trouble. I remember that. Miss Henderson, she got mad at me. All right, take a short break. We'll go to probably 5 or so. We got out of lab early today. Draw it out. You'll see it's got 3 charges.
Yeah, and then one of them negative.
One of them.
Is that
It's going to have to be 2 negative one time. Just one of the negative ones.
You know where, is that vertical?
it's in your paper?
Just use my debit card.
But do you know where I think it's close to Applebee's. Yeah. You know where the bowling alley is? It's like,
I really want to go find
Oh,
a serious
yeah,
building
okay.
and just
So it's next to like a wine.
I don't know why.
Well, first off,
I think so.
it's called Upfield.
Oh, it's called, if you
Shielded.
went to
I know what she likes.
Okay,
You come back with something, I'm gonna throw it at you.
We'll see.
That was
Talk
our
about
parents.
why things occur.
Oh, really? Oh, then yeah, it's right there.
That's what I was curious about.
That's crazy.
How what makes it sick?
The process of it, absorbing or relaxing, how.
Is it, do they have like vegetarian?
Which obviously.
Well, here I am. I'm a spin.
Probably, I mean, they probably have like.
And I'm sitting here.
More beans and rice and like
Um,
quesadillas and stuff.
If you want me to flip and go opposite,
Their
what has to be done?
salsa is really good.
Salsa?
Their
Has to
salsa is
absorb.
the Verde salsa.
So does it
Okay.
just read that change in energy?
Yeah, you gotta have to. Yeah.
Cilantro.
So the energy's got to come from somewhere. So throw me some energy. Just throw it out. Boom, I absorb it. But that can be gray. And that turns into the just like an IR. That's what that is. I mean, it's different energies that you're absorbing.
So I never even.
It's an absorbance clock.
I love it.
We'll, yeah.
I'm obsessed with it.
And how you know that's.
They have good, they have good
We're supposed to be able to
sushi
look
and
at
they
it.
have like really good.
Well, we got a long way to go. We covered the intro and the theory. We're going to look at the topics.
Yeah, that's it. I like to.
Integration of signal. That's the peak height. That's the area under the curve. Coupling, the multiplicity. That's why some things are singlets, some things are triplets.
No, what is that?
I read the section on books.
It's out in
Last,
What
well,
is that?
actually pre-course.
It's
We're trying to do pre-course sushi.
Oh, I want to go.
And how to count when you're given the structure, not how to take the graph and get the structure.
Right, you need to go the other
I
way
was
also.
worried because I thought it was going to be not for lunch, for lunch it's in the red and the
So Michael,
for all you can eat sushi.
what's your name? Peter? No, back here.
Yeah, Cody.
Cody?
Yeah. It probably says Michael on the list.
Yeah, it says Michael on the sheet. Okay, Cody. Yeah.
That's the question I was gonna ask earlier. If we're doing the mechanism, we just write.
We used to.
I've been there.
You're doing synthesis.
When like behind.
Oh,
Asian place?
You're doing predicted product.
No.
It was by.
Teach me about that.
Step
one
I don't
was
No, this one's on the
chloride.
The problem was asking you to show the product.
It's like.
You You need to think
I don't really
mechanistically.
know how I
Right.
found
But
it.
you don't have to show it
I
out.
think someone.
Only if you were asked a mechanistic question.
Oh, it's the
Super
bill. Is it really?
Safety stuff, do you want lines drawn blank?
There is.
No way.
Guy who's executing.
Seriously.
It's what it says in the book.
No, it's not the actual plan.
Okay, you want to put some on it, and then
This place is really tiny.
just let it fall, kind of towards back and forth.
Oh, you need to do it. I'm gonna try that.
I'm just trying out
Great faster, it'll work in like 5 minutes.
You can have the shish kebab.
Oh,
Yeah, they have like, they're great food. They're really good. But they're,
Okay, guys,
they're so good.
I didn't show the magnet up here, did I? I'll bring these smaller magnet. Here's a bigger magnet. Here's a smaller magnet. This would be a bigger magnet. Put the sample in. This would be like one of the nuclei in the sample. There it is. If I had 20 of these, they'd be all random, right? I should bring 20 of these. Pretend they're all random. And that thing has a direction because one end is different than the other. And usually you can't tell that until you start doing something like this. Okay, that's all random. What if we put it in the presence of an external magnetic field? I'm going to bring the field here. What happens to that? You see how it lined up? Now it's lined up. Okay? It actually lined up that way. What if I try to turn this around? And so now it's going to oppose. It actually doesn't want to line up. That's high energy. But see, a proton, a nuclei will. Because the energy difference is so small that it will actually, it'll do it. So you get population in both the alpha and beta states. Okay, here are the topics. The first is number of signals. We've already kind of done this some, right? Let's just do some more examples. Everybody back? If not back, say something. All right, number of signals. Now, the first half of these, the answers are already there. We'll go through them kind of quickly. And then the bottom half we'll do on our own. This is just like this alcohol here, yeah? Yeah. Okay, 3 different types of hydrogens. Where this one had 4 because there was an H on the oxygen. A, B, and C. This is like the alcohol. The 2 on the outside are the same. We have symmetry. So they're both A, and then you have the, did I tell you what the CH is? What's a CH2? Methylene. A CH is a methine. Meth and an INE. You don't have to know that. Free information. Okay? Methylene. This methine is different from the methyls. How many signals here? This is an ether. What's that? Ethyl, methyl, ether? A, B, C. That methyl is not the same as that, is it? That was bonded to oxygen. That was not. 3 signals. How about dimethyl ether? How many proton signals? 1. Both methyls are the same. What is this? Methyl butyl ether? Gas additive used to be. How many signals? These 3 methyls are the same. They're all on a carbon that's bonded to an oxygen, and this methyl is different. 2 signals. And once we start talking about integration, the A signal will integrate for 9. The B signal will integrate for 3. That's your number of hydrogens. Just another example, 2 here, right? Like 2 different proton signals. How about an alkene? How many signals? Is this methyl the same as that? Yeah. Here you can clearly see the symmetry of this here. That methyl is mirroring that methyl. They're the same. That H is the same as that H. You got the signal for the methyl and the signal for the 2 H's. 2 signals. How about this guy though? How many signals? The answer's already there, but see, that was 3. Is this H the same as this one? No. Obviously not, A and B. Why are they different?
B is closer to bromine.
A is trans to the bromine, that one's cis. And the pi bond restricts to rotation, it's stuck that way. You do have through space effects. This one's closer to the bromine just through space. These are different. If that was an alkane, it would be same because of free rotation. There would be another H there also. And then that H is different from the others, right? It's on the same carbon as the bromine. 3 signals. Benzene, how many signals for proton?
1.
Just 1. Does everybody agree that all 6 of those hydrogens are the same? Benzene has lots of symmetry. How about nitrobenzene? Major component in old-fashioned shoe polish. It really smells like shoe polish. If you look at here, these 2 H's are the same. This is on a carbon that's next to a carbon with a nitro. This is on the carbon that's next to a carbon with a nitro. Those are the same. These 2 are the same, and then that one is different. You do have symmetry through here. So 3 signals. Okay, we're ready to do some on our own. Okay, you guys on the right over there, my right, do the first one, and then the first with the benzene ring. You guys on my left, do the second one there, and then the second one with the benzene ring.
Think of
How about the first one? 2? Anybody got something different? 2. A, B, what's this? B prime, or it's the same thing. A prime. You got A's and B's. The methyl on the end is the same as that methyl on the end. That methylene is the same as that methylene. You have symmetry there. 2 signals. Okay, over here, guys. This would be called, that's butane. This could be called, well, how many signals? 2. 4. Haven't heard the right answer yet. 5. Who said 5? 5. CH3. CH2. Is this CH3 the same as that one? No. So I'm going to say C. How about this CH? D. Where's the 5th one? You didn't see it because the H was drawn in. Is that right?
Yeah, for mine.
A, B, C, D, E. H is on nitrogen, right? Don't forget about it. Okay? Why'd you miss those?
I forget about the one that's like connected.
Yeah, I forgot about the.
Oh, did you miss that one?
Yeah,
Yeah.
There is one H there, yeah?
forget about that.
There's one H there. Okay, guys over here, how many for this benzene compound?
Four.
4. Is H, 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 H. A, B, C, D. What was this, 5? Yeah, this is 4. That H is next to chlorine. Is there any other H next to chlorine? No. This H is 2 away from chlorine. Any other H 2 away from chlorine? That H is 2 away from bromine. You see, see? They're all in different places. There's no symmetry there. 4. How about this guy over here? 2. A, B, what is this? A prime, B prime. The H there is the same as the H there. You have symmetry. Both of them are right next to the chlorine. Here you have symmetry. How about the one on the right?
1.
Good. 1. They're all 4 are the same. So you have double symmetry there. All 4 of those are the same. Same chemical environment and thus same magnetic environment. That means they experience the same magnetic effects due to the electrons. And thus, that B local is going to be the same for all of them. And thus, the B effective is going to be the same for all of them. They experience the same amount of magnetic field. They all absorb at the same exact energy level and give one peak. Eugenol. It's kind of just a synthetic precursor. It may be a natural product in something. I put it on here at the time because I was going to develop a lab using eugenol, but I've never done it. How many signals for eugenol? And the proton NMR. Let me see. 9 looks good. H there. H there. Are those the same?
Yes.
They're not. This one is cis to the group coming off the alkene. That one's trans to the group coming off the alkene. They're different. So I'm doing A, B. I can't count A by A, B, C. So I'm going to say 1, 2. That one is different. That's 3. You got these here. They're identical, but they're different from those. So that's 4. That's 1 signal. They're identical. So 1 signal. Got that one. What's that? 5, 6, 7, 8.
9.
Phenol. 9.
What about the one below the 08?
See,
Right there?
Oh, it's 4. Okay. Never
Yeah,
mind.
that's a
It's
double
no
bond
8.
there. It's,
Okay.
it's not, it's kind of quickly drawn in.
Yeah, yeah.
Benzene ring, if there's a substituent on the benzene ring, there's no H on the carbon. Integration will be 1, 1, 1, 2, 1, 1, 1, 1, 3. When we get to integration, that's the number of hydrogens for that signal. How about phenacetin? Some of you made phenacetin inorganic 1? Yeah? Hi guys, we didn't do that. Usually I do it in organic 2 at the very beginning, but because some of you did it with Dr. Adele, we're not doing it here. How many signals in the proton NMR? Phenacetin, by the way, is made from acetaminophen. How many letters are right here? A, B, CH3, CH2, different. C, what is this? C prime. You have symmetry here. A benzene ring that has two substituents opposite, which is called para, is always going to have that symmetry. This is D, D prime, E,
And then the.
and F. How many we got? 1, 2, 3, 4, 5, 6. Did I miss something?
Does it matter between letter, like, if I started at the other end?
No, we're just keeping track by letters. Did we get it right? 1, 2, 3, 4, 5. Is there 6? 6 protons. 6 signals in the proton NMR. Let me ask you this. How many signals if we were doing carbon NMR? The question is essentially how many different types of carbon in the molecule? 6 H NMR. How many carbon NMR? And usually this is written like 1 H NMR, and this is written 13 carbon NMR. I'll do this one with numbers. I see this carbon here, that's 1. I see that carbon, 2. See, that's a carbon. There's no H there, but it's a carbon. That's 3. That one's 4. What is this one?
Same.
That's 4 prime. That's 5.
5 prime.
5 and 5 prime. These carbons are identical. 6.
So second.
7.
Oh, no, the double bond is on.
Double bonded up.
Don't forget that one. That is a carbon. 8. Eight signals in the carbon NMR. Look on the next page and see if we got it right. Which one's the proton NMR? How you notice the one on the top? 0 to 10, 0 to 12. If you look at the baseline on the one at the bottom, it goes what? 0 to 200. Also, but we'll mention it in a minute. How many protons did we expect? 6. Here are your 6. 1, 2, 3, 4, 5, 6. Different shape. One of them's a little tiny, kind of broad little guy here.
Why is it on there?
That's the NH. We're going to learn this is the aromatic region. These are hydrogens on aromatic ring. We're going to learn that this is more of the saturated alkane region. I can ask you this here. If we go back and call that A and that B, which one is B? My left or right? Which one is this, A or B?
That should be
The
A.
more unshielded one.
Is the option?
That should be.
Again, I said that's A and that's B.
So B That's B.
This is B. The oxygen is de-shielding it. It's pulling the sunscreen away from it. The electrons away from it. What does that? How does that move the signal? Downfield. That's actually B. This is here is the A, the terminal one. This is the CH3 up there on the carbonyl, the amide. And it's actually a singlet. The reason it's real tall is because it's 3 H's. We'll get to that. How many carbon signals did we expect? How many we got? You got 8. What do you see in the carbon that's real different from the proton in terms of peak shape? Carbon NMR, they're all singlets. They don't have to be. We do that on purpose. We remove the coupling. That can be done. Because usually we want to simplify the carbon NMR. If you kept splitting, it gets so complicated. So somebody along the way said, we got to figure out how to get rid of this splitting, that phenomenon. And they figured out how to do it. 8 signals. Same terminology. These are more downfield. Thus, these are going to be more de-shielded. Carbon NMR will be another handout. Okay. Peak position. Next topic. And yesterday, we didn't get to go much further than we're going to introduce this because people were trying to get in the room at 4:30 yesterday, and we had to leave. So I'm just going to introduce this, and then we're going to stop, same place as we stopped, said yesterday. I used to have Thursday left on Wednesday. Okay. This is an introductory table for peak positions. Then you'll see a very detailed table. You have to have knowledge somewhere in between. The detailed table is really there for reference. All right. Types of hydrogens, where do they absorb? You'll notice these generic molecules, upfield, low ppm value, these are all going to be your H's that are on sp3 carbons. Over here. If it's just a plain alkane, like butane, it's going to be around 1 ppm, 1.5. To get the peak to move that way, you have to have some type of electron withdrawing effect, like a halogen or an oxygen. Let's skip this. Let's go over here. This is an example where the carbon, instead of just having H's on it, it has something like a nitrogen or oxygen or halogen, which would act as a greedy electron puller. That would de-shield this area, move the signal down. You get down to about 3 to 4 ppm. But it's still an sp3 carbon, so it's still here. In the middle is a CH that's not bonded to like a bromine or something. It's bonded to a carbon that's double bonded. And the most common is, that's oxygen, or that's a carbonyl. Next order of carbonyl is going to be about 2 to 3 ppm. Because it is pooling, you do get to kind of the pool, but it's not as great as these heteroatom pools. And there's a little bit going on. The pi system may act a little bit like shielding. Okay, so sp3. If the H is on an sp2 carbon, you're going to be more like downfield. Alkene region is like 5 to 6. H on an alkene. If the H is on an aromatic ring, we go downfield even a little bit more. We get about 7 to 8. Now that 7 to 8, can it really be maybe 6 to 9? But usually people say 7 to 8. We have a couple of particular ones. The H of an aldehyde is like about 9 to 10. And really there's nothing else really there. The H of a carboxylic acid tends to be downfield, although it can be variable. H's of alcohols and amines are not shown here. There you go. That's the one we didn't say is, it's actually kind of an outlier. We say sp3, sp2. You might expect that an H on an sp carbon would be here. Actually not. An H on an sp carbon, alkyne terminal H is actually about 2. And we'll say why. It's because these electrons in this triple bond actually have a shielding effect. It keeps it here. Where these electrons have a de-shielding effect. It has to do with the direction of the field that's generated there. It's called anisotropic effects, directional effects. It's on the next page. It's a minor point, but it's just kind of interesting to explain this trend. This is about where we stopped yesterday. Let me show you. Yeah, that's pretty much. I don't even think we looked at this next table yesterday. It just gets more precise. Again, you don't want to sit down and just memorize every single number. You want to definitely know the starting trends. As you work problems, you'll use the more precise tables. What else can we say here? We won't do an MR class for like almost 2 weeks. Okay, we'll do this at the end, right before test 1. I usually didn't do this initial lecture at all, but to only present NMR and give you a week before the first test, you needed more time. So we do this, I give you a week and a half or 2 to be working on it on your own. We'll come back and we'll finish this up in a couple of weeks. Like five lectures or so. There's problems in the workbook. You'll see comprehensive spec problems like in there. Any questions, guys? We'll get out of lab early today. How about that? Not too bad, yeah? Not gonna learn it all right here, but you know, it's a lot, but it's good science, good fundamental stuff. There's a lot of physics involved if you're interested in physics. Have a good weekend, guys.
Thanks, sir. You too.
All right.